Hello everyone and welcome to this online video tutorial for the electromagnetism course in UCD. This is PHYC 30070 and in this tutorial I want to go through the solutions to the assignment 3 problems. This is all good practice for the final exam. Many of the questions in these assignments are taken from previous exam paper questions. So let's get right into it. In assignment 3, question 1, we're asked to compare and contrast electrostatics in conductors and insulators, making reference to the behaviour of the electric field and the electrostatic potential V, and any induced or bound charges. Use diagrams, equations, and examples in your answer. So I'm not going to write out an essay here, obviously, but this kind of question does feature often in the exams, or at least part of a question in the exam might be something discursive like this. And the idea of these questions in the exam is to really get you to write out what you know. So it's an opportunity for you to say all the things that you've learnt in a kind of unstructured way, so that the question is not leading you in any particular direction. You can choose what to present. And in some ways that's nice because it gives you the control, but in other ways it puts the responsibility on you to kind of have prepared or have up your sleeve something that you can write about. So it's a good idea to think about these kind of discursive questions in advance of the exam. There will always be some kind of question like this in the exam. And in this one, it's about electrostatics, and we're asked to compare and contrast conductors and insulators. So on a heuristic level, this is obvious. We know what a conductor is. It's something that conducts electricity. We know what an insulator is. It's something that doesn't. There are many ways in which we could compare and contrast this, but the point is we've got to do this from the perspective of electrostatics in this question, and it tells us specifically to make reference to the electric field and the potential. So let's get right into it. Let's make maybe a little summary of the various things that we know about conductors and insulators. Let's start with conductors. So in your answer, you should of course write this out in some kind of coherent, discursive essay. But here I'm just going to sort of summarize the things that you should be talking about. The important thing about a conductor is that the electrons inside the metal are free to roam around the material, and we assume that we have sort of an infinite amount of this free-flowing charge. And that free-flowing charge responds to external electric fields. So if I put the metal in an external electric field, then due to the Lorentz force, the electric part of the Lorentz force, the electrons will feel a force in the direction of the electric field, and they'll move in response to the electric field. So those electrons begin to move. That's a current flowing in the material, and they do this rather quickly, but then they reach the sort of edges of the material, and you get like a pile-up of charge at the edges of the material, and the charge distributes itself in such a way to cancel out the external electric field within the material. Why? Because the electrons will adjust themselves, the positions of the electrons in the material, until a point when the electric field inside the material is zero, and then when it does that, there's no force, and then everything settles down. So sort of by construction, the electrons move until they no longer move, which means the electric field inside the material is equal to zero. So because of the free-flowing charge, we have that the total electric field E is equal to zero inside. And that's really the key point about conductors in terms of electrostatics. Everything else that I'll talk about flows from that condition. If the electric field is equal to zero, that means the potential is constant within the material. So that means the material, the conductor is an equipotential. A special case of this is if the material is grounded. If you connect your metal to ground, then that's basically equivalent to saying let's set the potential not just equal to any old constant, but equal to 0. This is all slightly a matter of taste because, as you know, the potential is only defined up to a constant. So whatever constant it was, we could set that to be the reference point for our potential. But by convention, if it's grounded, then we set that constant to 0. What else do we know? We also know that the electric field, of course, is not 0 outside of the material, and in fact the electric field is perpendicular to the surface of the material immediately outside. So we have an expression like this, which tells us that the electric field depends just on this perpendicular component, where this n hat here is a unit vector perpendicular to the surface. And if I were to draw a little cartoon, we could have some material like this. Inside, we have that the electric field is equal to 0, but outside, we see that the electric field is proportional to the unit vector normal to the surface. So you have something like this. Now, of course, we have this situation precisely because the material is in an external field, and the external field lines could be something like this. Let's see, for example. And of course, the electric field lines have to be continuous, and so because of these perpendicular field lines around the material itself, the external field lines must be distorted in some particular way. So the external field lines that I've drawn here have to somehow become distorted near the material itself. What else do we know? We know that because the electric field is discontinuous at the surface, that arises from the simple fact that it's 0 inside the material and generically non-zero outside. But the potential is not discontinuous. The potential is always continuous. And the potential is always continuous because we need to take the derivative of the potential to get the electric field. And if the potential was discontinuous, that would correspond to an infinite electric field, and then we'd need an infinite force to push a charge through that part of the system, and therefore that's a non-physical kind of situation. So the potential is continuous, and furthermore, we can take the derivative of the potential perpendicular to the surface, and that should give us exactly the electric field. And we can relate this to an induced surface charge. So we imagine taking the derivative of the potential in the direction of the unit vector normal to the surface, evaluated at the surface. We can always do that because the potential is continuous at the surface. And this will be equal to the induced charge at the surface. So an example of this would be, let's consider we have some spherical ball of metal in some external field. Then in response to this external field, the electrons redistribute themselves in such a way to cancel the external field, something like this. And then the negatives go in here. Why have I drawn it this way around? Because the electric field lines go from positive to negative. So this would be the induced electric field going in the opposite direction, and the magnitude of that is exactly to cancel the external field. But you see implicitly here what I've drawn is these pluses and minuses here. This is precisely the induced charge here. And we can calculate that through the derivative of the potential. Maybe one other thing we can say, let's imagine that we have a material and we have a cavity in the material. Then in an external field, we have this distribution of charges somehow. And then we'd also have some distribution of charges on the sort of interior, or this part of the cavity here. And again, the charges arrange themselves in such a way that to cancel the electric field inside the material. But that actually implies something else for the cavity. It tells you that there's no electric field inside the cavity either. If there are no free charges inside the cavity, at least, there's no electric field in the cavity. And that's the principle of the Faraday cage. Okay, so here's some equations, here's some physical situations, here's an explanation. So you need to convert that all into an essay. The essay, you shouldn't use many words in the essay. Just try to get across the key ideas and use lots of equations and diagrams. Also, notice how many marks this kind of question is worth in the exam. Do a quick back of the envelope calculation to work out how long you should be spending on that question in the exam. So don't write an essay that takes you 1 hour if it's only worth 10 minutes of your time. So be careful to make sure that you're looking at the clock and making sure that the effort you're putting into a given question is commensurate with the marks you're getting from it. What I wrote down here was a summary for conductors. Let's now switch to insulators, and then finally in your essay you should sort of actually make a comparison between the two to bring it all together. So let's now switch to the discussion of insulators. So for insulators, the situation is rather different. So for insulators, we do not have an infinite amount of free-flowing charge in the material. The electrons are tethered to their respective nuclei. They're not free, they're localized. However, they can move a little bit, and the collective motion of all of these tiny displacements of the centers of the negative electronic charge around the centers of positive nuclear charge give rise to a polarization in the material. This polarization changes the electric field inside the material and outside the material, but the electric field doesn't totally vanish inside the material, unlike in a conductor. So this polarization is what we want to discuss. The external field polarizes material. And this causes a polarization field P. And we regard this really as a field in the sense that we imagine that it exists everywhere in space and in time. The polarization will be zero outside the material, obviously, but it will be finite in general inside the material. And we can imagine that we have a small dipole moment, which is the polarization, big P, times d tau, the volume element. So this is the dipole moment. And we imagine that this dipole moment is something that's microscopically arising from the displacement of the electronic and nuclear charge due to polarization from the external field. But the charge is not free enough that it can totally escape the nucleus and just roam around the entire structure. If we have a linear dielectric, which is admittedly a special case, a common but special case. Incidentally, these materials in the context of electrostatics are called dielectrics. they are insulators. So these linear dielectrics are ones that have a special property, namely that the polarization field P is actually proportional to the applied electric field, or the electric field, I should say. This is the total electric field here. So that helps things enormously, but that's not always the situation. It's a special case for linear dielectrics. The electric field inside the material is not always zero, not in general zero. And indeed, because of that, the potential is not constant. So it's not an equipotential. So if the electric field is not zero, what is it? Well, we can determine the electric field from the so-called bound charges, and we can kind of pretend that the material itself and all the microscopic complexities that come with that, you can pretend that the electric field from such a system is actually just due to a simplified system of bound charges in the bulk of the material and at the surface. And this is basically the uniqueness theorem. It's saying, provided that you have the right boundary conditions and the right charge density, then you can think of a different system that gives you the same potential. So these bound charges there's one for the bulk, rho b, and that's given by minus the divergence of the polarization field, and there's one on the surface, sigma b, b for bound, which is the polarization field at the surface dotted into the unit vector normal to the surface. So this kind of plays a similar role to the induced charge at the surface of a conductor. Here you have a bound charge at the edge of the conductor due to the polarization of the material. The difference is, of course, that you can also have a bound charge in the interior of the material in insulators, giving rise to a non-zero electric field inside the material, and that's this rho b. And that's the kind of properties that you get from an insulator. So the total electric field inside the material and outside the material is a combination of the external field plus the material's response. And the material's response is determined by the polarization through these bound charges as written. The electric field perpendicular to the material is discontinuous. Why? Precisely because we have a bound surface charge. And we know that the electric field is discontinuous across a charged surface. So this bound surface charge really plays that same role as a charged surface. However, you'll see that the bound surface charge is controlled by this polarization dotted into the normal vector to the surface, and that has the implication that the parallel part is continuous. It would be good to come up with a few sketches and examples of situations like this, where we put in, for example, a dielectric sphere in some external field and just plot what kind of field lines or bound charges you might expect from that. Another kind of thing you could imagine is a dielectric material with some free charge. Let's say we put in this material a charge Q and ask what happens. The charge Q, of course, generates its electric field due to the Coulomb law, and the that electric field will polarize the surrounding dielectric material, and it does so in such a way to kind of cancel out the effect, or partially cancel out the effect of the electric field, as you might expect. And so if this charge Q is positive, what happens is the material becomes polarized by having a polarization field set up, which looks basically like a set of induced charges. That's actually these bound charges here, which are coming from the divergence of the polarization field. The polarization field is definitely diverging because we have a point charge with diverging field lines coming out of that, and the material will respond likewise. So we'd have a bunch of bound negative charges close to the embedded point charge, and then a corresponding bound positive charges sort of further away, which have sort of arranged themselves to counteract this this external field and are arising due to the polarization of the material. And the result of all of that is that the charge Q is partially screened, electronically screened, and this is the sort of dielectric effect. That's because we have loads of negative charges very close to the charge Q, and then the compensating positive charges. Of course, the material is overall net neutral, but the positive charges are further away, and so because we have an inverse square law for the electric field and forces, it looks like the charge Q is weakened in its effect. So these are the kind of examples you could imagine discussing, and there are other ones, and I leave it to your ingenuity to come up with them. So you see, these kind of questions are just a bit of revision, if you like, to get you thinking about what are the important points and to compare and contrast these different situations. Okay, so let's move on to question 2. This is putting into application some of the concepts you were discussing in question 1 for dielectric materials. A solid sphere of radius r carries a frozen-in polarization, and we're given this as P, which is polarization field, notice P of r, is kr, so it's something that is radially directed. Where k is a constant, r is the vector from the centre, so implicitly here we're locating this solid dielectric sphere with its centre at the origin of our coordinate system. In part A, we have to choose an appropriate set of coordinates and draw a sketch. Well, that's quite easy, at least, so let's do it. I'll draw my dielectric sphere in red, and we can put in here some coordinates. These are Cartesian coordinates, but we may wish to, in this case, switch to spherical polar coordinates, and that's because, of course, this thing has spherical symmetry. The solid sphere itself is something of spherical symmetry, but also the polarization field is also radially directed. So we would have a r theta and sort of phi angles and radius here to describe our system. So that's the kind of setup we want. The sphere itself is of radius capital R, and we have a polarization P, which is some constant K in the R direction. So that's all nice and simple. In part B, we are supposed to calculate the bound surface charge density and the bound volume density. This is putting into action what we were just discussing a moment ago. So if we want to know the bound surface charge, this is the polarization field dotted into the normal vector at the surface. Because this is a sphere with the origin, with the centre at the origin, the normal vector to the surface is the r hat vector, and given that P is along R, this is dead simple. we just get kr, and this is evaluated at the surface, which means r is equal to big R. So in the end, the whole thing is just kr. Pretty straightforward. And so that's a constant around the surface. There's no theta or phi dependence to that. Then we have the bound volume charge density, rho b, and this is minus the divergence of the polarization field here. And here we have to be a little bit careful. We're going to use the spherical symmetry of the problem, so we need to know the definition of the divergence in spherical coordinates. And so we turn to the formula sheet, and it's written there how to do this, and we copied it out. It's minus 1 upon r squared d by dr of r squared times the polarization in the radial direction. Now, when you're calculating the divergence, there are other terms, of course, for the angular components, but we don't have an angular component to the polarization, it's just radial, and so we leave it at that. So the polarization in the r direction is k times r, which is pretty straightforward. So we take the derivative of this thing with respect to r, divide by minus 1 upon r squared, and we get also a constant, minus 3k. So we see that there's a constant bound volume charge within this dielectric sphere, and we see that there is a constant bound surface charge, and those two things are different. In part C, show that the net bound charge is equal to 0. Now, this must be the case for physically obvious reasons. The material started off being charge neutral, and these bound surface and volume charges are just the consequence of a redistribution of the charge, so no charge is created or destroyed. So if I integrate these things, the sum must come to 0. It's just a redistribution of the charge. So what we have to do is integrate the bound surface charge over the surface, and integrate the bound volume charge over the volume of the sphere, and then add those two things up. So let's have a look at the net charges. Let's call the net surface charge Q surface. That's going to be the integral over the surface of the surface charge density rho b, integrated over the area dA, and we've just worked out the surface charge density, which is kr, and we know the surface area of the sphere, which is 4 pi r squared, and r is capital R, so I can just do this directly. Of course, I could convert this into spherical coordinates and do the angular integration and all of that stuff, but because the surface charge density is a constant, I know that the total surface charge is going to be the surface charge density times the surface area, which is 4 pi r squared. So I can just write down the answer without further ado. 4 pi r squared times another r from the charge density, and then k coming from this k in here. Very good. Let's look at the volume bound charge Q vol, let's call it, which is the integral over the volume of the sphere of the volume bound charge, which is minus 3k t tau. Again, I can convert this into spherical polar coordinates and do the integration, but again, for the same reasons, it's rather more simple than that, because the bound volume charge is a constant, And we know that the volume of the sphere is 4/3 pi r cubed, with r being capital R, the radius. And so again, I can just write down the answer. It's minus 3k times 4/3 pi r cubed. The 3's cancel, and I get minus 4 pi r cubed. And of course, the whole point is that these are positive and negative of each other, such that the total charge Q, which is the surface contribution plus the volume contribution, is obviously equal to 0, as it always is. So this is a sanity check, if you like, on your answers. Part D, calculate the electric field inside and outside of the sphere. We have spherical symmetry in the problem. So the electric field is already something that we can write down in this form. The electric field at a point r in space can only be something in the r direction because of the spherical symmetry. It only depends on the radial distance from the origin rather than the r vector, and it's directed in the radial direction, r hat. So in this simple equation that I'm writing down here, that might seem rather obvious, we're actually making quite considerable use of what we know about the system in terms of the symmetry to simplify things to rather an extraordinary degree. You might not think that this looks like very much, but we actually achieve quite a lot here. We're saying the direction of the electric field is radial. Only that component counts in the vector field. And furthermore, the magnitude of the radial component of the electric field only depends on the radius. It doesn't depend on theta or phi in spherical coordinates either. So how are we going to extract this electric field? Well, we're going to use Gauss's law. And Gauss's law tells us that the electric field flux through a Gaussian surface of our choosing is equal to the charge enclosed within that Gaussian surface divided by epsilon naught. So what Gaussian surface are we going to choose? Well, we need to pick one that's commensurate with the symmetry. In particular, we want to pick a Gaussian surface where the normal vector, so perpendicular to that surface, is parallel to the electric field lines. We want to do that because in this integral we have E dot dA. This is the vector area, and the vector in question is perpendicular to the surface. So we want to pick a surface such that E dot dA gives us a scalar quantity E dA. We want the electric field and dA to be in the same direction. We also want the electric field to be constant everywhere over the Gaussian surface, and we can do that, both of those things, very simply by picking, quite obviously, a Gaussian surface with its, which is a sphere centered on the origin, which is the center of our dielectric sphere. And that Gaussian surface will be a sphere of radius r. And we can consider different radii for this thing. Let's first of all consider the situation for the electric field outside the sphere. That's one of the things we've got to do. So this is where this r that I'm considering is going to be greater than the radius of the sphere, capital R. And what is the charge enclosed? The answer is 0. We just worked out the total bound charges for the entire thing, and we discovered that the total bound charges were 0. And that's always the case. It's a general property. If we have a dielectric material, which was originally charge neutral, then any kind of polarization in that material doesn't change the amount of charge. The net bound charge is equal to 0. And so if we add up all of that, the total charge is equal to 0. The enclosed charge is equal to 0 if we just have a polarization in our object and there's no free charges. We're just talking about the bound charges. So when we're outside of the sphere, the charge enclosed is 0. And that implies very neatly that the electric field is equal to 0 outside the sphere. Maybe not completely obvious that was the case, but that is indeed the case. What about inside the sphere? So this is where our R is less than big R, and in particular, because we're looking inside the sphere, we don't count the bound surface charges, and therefore there will be a net charge when we're inside the material because the bound surface charges are not present in the calculation. So we just do the calculation. What is E dot dA? By exactly the same logic as before, it is 4 pi r squared, where the r here is now the radius that we're interested in, the radius that we're looking at the electric field for, not the radius of the sphere. So it's 4 pi r squared, little r, times the electric field at that, across that surface. And again, the point is that that's constant at this radius, and it's also in the radial direction. So I just get this simple expression. That whole thing is equal to the charge enclosed, divided by epsilon naught. What is the charge enclosed? Well, let's work it out. We do a volume integral of the bound charge, d tau, over the particular radius of the sphere that we're interested in. And it's the same kind of calculation as before. It's going to give us minus 4k pi little r cubed. And again, it's little r. And so putting that together and rearranging a bit, we can extract the electric field inside the sphere as minus k upon epsilon naught in the r direction. Note that the electric field is discontinuous across the surface. That's precisely because of the bound surface charge at the surface of our sphere. Okay, so let's consider question 3. It's about a coaxial cable, and I've taken the liberty of sketching it here. It says in the question, a certain coaxial cable consists of a copper wire of radius A, and that's this thing in the middle here, and I'll just draw on this radius A here. And it's surrounded by a concentric copper tube of inner radius C. So this is the outer radius here, radius C. The space in between these two copper structures is partially filled from B to C with a material of dielectric constant epsilon r. So this inner radius here is B, dielectric constant epsilon r. So what we've got to do is find the electric displacement d between the two conductors. That means between the radius A and C. And then once we know that, we're going to work out the capacitance per unit length of the cable. So this kind of cable is called a coaxial cable because we have cylindrical symmetry, and there are two cylinders with the same axis, so they're coaxial. So first of all, we want to let the charge on the inner conductor be Q. Let's write that down. So let's let Q be the charge on the length L of the cable, let's say. So we should be specific about what we mean. Q will be the charge on the inner conductor, and it'll be on the length L of the cable. And what we're going to do is use Gauss's law for dielectrics. which relates the electric displacement to the enclosed free charge. And importantly, we see here that this electric displacement is something in this integral. It's the flux, if you like, of the electric displacement through the given surface. And again, we construct a Gaussian surface here, which of course should also be coaxial to respect the symmetry. And we'll construct a Gaussian surface of radius r. So this Gaussian surface is going to be a cylinder, a coaxial cylinder. In cylindrical coordinates, often we call the radius s, so let's call it a radius s to disambiguate it. And this object is easily computed. We can write this simply as 2 pi s times L over a length L of the cylinder times the electric displacement d. And that is because the electric displacement will be radial in the s hat direction, and the unit vector normal to our Gaussian surface is also in the s hat direction. And because the electric displacement only varies according to the distance from the axis rather than any angular dependence, we can simply take that out of the integral. The remaining integral is then just the area of the cylinder, which is 2 pi s L. Good. And on the right-hand side, we have the charge enclosed, which is simply this Q that we've just defined. And so putting all of that together, we learn that the electric displacement is Q over 2 pi s times L. And if we want to convert that back into a vector, the electric displacement is, of course, a vectored quantity. Then the magnitude of that vector is this quantity, Q over 2 pi s L. And of course, that's in the s hat direction by the cylindrical symmetry of the problem. So that's the first part of the question done. Very simple. Our result here for the electric displacement is actually valid in a specific regime. S must be greater than A, and it must be less than C. And that's because what we've done here is use Gauss's law. The charge enclosed is the charge on the inner conductor, that's Q. And therefore the radius needs to be greater than A so that we encompass the full charge of the inner conductor. However, the radius should also be less than C, the radius of the outer conductor. If S is greater than C, we'd also have to take into account the charge on the outer conductor, which we don't know. So this result is valid in the regime of radius between A and C. Now what we want to do is to determine from this the electric field, and we can do that because we have a homogeneous region of space filled with dielectric. Either between A and B we have a vacuum, or between B and C we have a dielectric with dielectric constant epsilon r. So in both of those cases we can just write down the electric field. So the electric field has to be computed piecewise for these two different situations. One is where it's Q over 2 pi epsilon naught S times L. That's in the vacuum region where the radius is between A and B. Or we have Q over 2 pi epsilon naught times epsilon r SL, and that's the result that's valid within the dielectric, a radius between B and C. So we have two different results for the electric field depending on what the dielectric constant is. Now, to be able to compute the capacitance, which we're asked in the last part of the question, we're going to need to relate the charge to the voltage. The voltage is, of course, the potential difference, and therefore we need to compute the potential evaluated at A and the potential evaluated at C, because the voltage is of course applied between the inner and outer conductors of the coaxial cable, so that the potential difference between radius A and C is of course the voltage. And given that we know the charge on the inner conductor, if we know the voltage, we can work out the capacitance. So that's the kind of logic, if you like, that we're going to apply. And we can obtain the potential as the integral of the electric field, and we've just computed the electric field. So I'm going to break down the integral into two pieces. From A to C, we can break this down into an integral from B to C, and I can write down the electric field expression from B to C. It's 2 pi epsilon naught epsilon r s l. And the path I'm going to choose, dl vector, is going to be along the radial path. That makes eminent good sense, so we're going to choose that one. And then the second contribution is from A to B, and the electric field in that case is q over 2 pi epsilon naught sl. Again, I'll choose the path along the radial direction. And so these integrals are rather easy. They're just basically up to some constant, the integral of 1 over s ds, which is log s. And then we have to evaluate it at the various limits. And it's fairly easy to show that this is going to be minus q over 2 pi epsilon naught l into, and then there's one contribution from B to C, that's within the dielectric, and then there's one piece from A to B, which is a vacuum, which has a dielectric constant of 1. So we have something like this. For the voltage or the potential difference between the inner and outer conductors. And the last step is just to convert this into a capacitance per unit length. So the capacitance, C, per unit length divided by L is therefore the charge per unit length, Q over L, divided by the voltage. And we've just worked out this potential difference, this voltage, and it involves the charge Q. So when I take the ratio of Q divided by V, that's going to drop out. Also, the potential difference involves the length of the tube, and that will also drop out. In the end, I'm just going to obtain this. It's 2 pi epsilon naught over 1 upon epsilon r log c upon b plus log b upon a. So it's just a bunch of constants that featured in the original problem statement. So we just see that this capacitance per unit length is a pure geometric factor, as we'd expect. So the logic with these problems is always to work out the electric displacement d. You do that for Gauss's law for dielectrics. From that we can work out the electric field, but you have to be careful with this because the electric field depends on the dielectric constant, which is different in different materials. But with that in mind, we can calculate the potential, the electric potential, and from the electric potential, evaluated at different points, we can work out a potential difference, which is the voltage. And in the end, of course, the charge divided by the voltage is the capacitance, and that's what we've computed in the end. Okay, so the final question in magnetostatics here is about the magnetic field and the vector potential. So we're given two equations. The curl of the magnetic field is mu naught times the current density, and the fact that the magnetic field itself can be obtained as the curl of the vector potential. From these expressions, we're asked to show that the line integral of the magnetic field around a closed loop is equal to the current enclosed. So let's have a look at that one first. So this is question part A, subpart I. We're going to start from the curl of the magnetic field is mu naught J. Let's take the integral dA of this object on both sides of the equation. So I'm looking at the flux, if you like, of this object, the curl of B, through some vector area dA. And whatever I do to the left-hand side, I have to do to the right-hand side, so equally I should take the flux of mu naught J through some area A. Okay, so the reason why I chose to do this is because, of course, I know Stokes's theorem, and I can apply Stokes's theorem to the left-hand side. Stokes's theorem tells us that I can relate the curl of something to a line integral around the boundary of that thing. So Stokes's theorem here would allow us to convert the curl of B here to, over some particular area, to some line integral around a closed loop of B dot dl. And of course that's what we had in the question. So when I saw the left-hand side here, B dot dl, I was thinking to myself, okay, we need to use Stokes's theorem, convert this into an area integral involving the curl, and of course I have the curl of B here given in the question from this. So I need to do an area integral on the left-hand side. And of course that's very fortuitous because the area integral on the right-hand side, the area integral of the current density through a particular area, is of course the definition of the current passing through that cross-sectional area, which is of course in the end equal to the mu naught times the current enclosed by the boundary loop. So we can call that I enclosed. And that's the first task that we needed to accomplish. We have shown that the line integral around a closed loop of the magnetic field is equal to the current enclosed by that loop. Good. So that was very straightforward. What about the second part of the question? We're told that the magnetic field is related to the curl of the vector potential, and from this, supposedly, we should be able to show that the line integral of the vector potential is equal to the magnetic field flux. So actually this is basically the same calculation. I will first write down the expression B is equal to the curl of A, and I will now simply integrate both sides of the equation over some area. So this will be the integral of B dot dA, the vector area, and then integrated over that area. On the right-hand side, I'll have the curl of A integrated over the vector area on the same region. On the left-hand side, we have, of course, the definition of the magnetic flux. This is the field lines piercing through some particular area. So that's the definition of the magnetic flux. On the right-hand side, it's Stokes' theorem again. And Stokes' theorem tells us that I can relate this area integral of the curl to the line integral over a closed loop bounding whatever area we started with, and those two expressions are supposed to be equal, and of course that's what we had in the question. We're told that we're asked to prove that the line integral of the vector potential around a closed loop is the magnetic flux, and again that's what we've shown. So the first of these two expressions you will have seen before. This is a classic one that we use many times. The second one, maybe we haven't really picked up on that. It relates the magnetic field flux to the vector potential, and actually it's this second, less familiar one that's going to be important when we tackle part B of the question. You'll notice in these kind of questions, which are actually from previous exam questions, often when you have a multi-part question like this, A, B, C, and so on, often parts of the early parts of the question are often useful to the later parts, so do bear that in mind as a bit of exam technique. So let's have a look at part B. In part B of the question, we're asked to find the magnetic field both inside and outside of a long solenoid, consisting of n closely wound turns of wire per unit length on a cylinder of radius r, each carrying a steady current I. Furthermore, we should neglect longitudinal current and effects to do with the ends of the solenoid. So this is completely bookwork. This is something we did explicitly in the lectures. It's also in all of the books, so it's extremely simple. We have a cylinder here. Often, as you know, these solenoids are actually filled with some magnetic material, for example iron, which boosts the effect. But we have something like this, and then we have a wire that's wrapped round. Let me quickly sketch this, something like the following, and then maybe it flows out here. Let's give it a directionality. We'll put in a current here, which will flow around the loop like this, and then out the other end. Now, the question tells us that we're to assume basically that the solenoid is infinitely long, so we're not considering any edge effect. So we're not, obviously the magnetic field resulting from this current flowing will be a bit different if we're looking down here at the edge of the thing rather than in the middle, but we're just interested in the bulk effect rather than the edge effects. We're also told to neglect the longitudinal current. What does that mean? It means that we have a lot of wire wrapping around this coil, n closely wound turns of wire, it says. And yet you can see that after n of these closely wound turns of wire, the current has travelled up from this point to this point. And that's the longitudinal current, which is tiny in comparison to the circumferential current that's wrapping around the solenoid, and that's just because there's so many of these wire loops so closely wound. And we're neglecting that upwards drift, if you like, which is slow in comparison to the circumferential current. So they're the assumptions. So basically what this neglecting the longitudinal current tells us is that we can assume that each time the wire wraps around this cylinder here, we just take that to be a single wire loop. We don't imagine it to be a spiral, we just consider it to be a circular loop. And of course that simplifies everything quite considerably. And the way we prove this, as done in the lectures, let's do it again, is very straightforward. First of all, we'll consider a Amperian loop outside of the solenoid. That's situation number one. And when we're outside, we can perform Ampere's law. And Ampere's law is precisely this thing that we discussed in part A of the question, namely that if we take the line integral of the magnetic field around a closed loop, that's equal to the current enclosed, and there's no current enclosed here because it's outside of the solenoid, so that's equal to 0. And that's true for any loop outside of the solenoid. And what that tells us is that the magnetic field must be equal to 0 when outside the solenoid. And again, the reason why we get that is because this result, that the line integral of B around the loop is equal to 0, is true for any loop, for all loops, when we're outside. And so I can pick any combination. If I can pick any possible loop and it's always equal to 0, the only way that can happen is if the magnetic field itself is equal to 0 outside. Okay, very good. What about the second situation I want to consider, which is going to be partially in and partially out? And the loop, the Amperian loop I'm going to consider is something like this. And we can break down that Ampere's law for the loop into a piece that's inside and a piece that's outside. And the bit that's outside will be, the integral will evaluate to 0 because the magnetic field is equal to 0 outside. That's what we calculated in the first consideration. And what about the second piece then, the bit that's inside? Well, there we need to do a little bit of thinking. We need to work out what direction the magnetic field is going to be in. And symmetry arguments tell you that it's got to be in the z direction, i.e. pointing upwards in this convention, coaxial with this cylinder. You can also get that just from the right-hand rule. We know that magnetostatics is determined by the Biot-Savart law, and for a wire we have the right-hand rule, so we know that if the current here is wrapping around and the field is going to be pointing upwards. So the symmetry arguments tell us that the magnetic field is something that's, let's say, equal to Bz in the z direction. That's perfectly clear. And then I consider what's happening when I evaluate the line integral of that around this loop. You see these horizontal parts don't contribute because I'm doing b dot dl, and the path dl is perpendicular to the field direction, which is in the z direction. So it's only this sort of vertical bit here that counts. And so when I substitute that in here, I basically get, let's say this length here of the loop, this vertical length is of length L. I then have to integrate from 0 to L the magnetic field B in the Z direction. Actually, you can see here that the line is pointing downwards, and by the right-hand rule, the magnetic field is pointing upwards. So actually, by convention, I will have a minus sign in here. And then we have another symmetry argument, which is if we're neglecting the edge effects, we know that the magnetic field will be constant, independent of the position z when we're inside this solenoid. So that's basically just saying we have translational invariance as we go upwards and downwards when we have an infinitely long solenoid. So this result here is just minus BL. So because we have a constant field, we integrate from 0 to L, we just pick up a factor at minus BL. Good. And what about the current enclosed? We're using Ampere's law, and so we relate this thing to the current enclosed. That in the end is just mu naught n I times L. So mu naught times the current enclosed. The current enclosed is the current around each loop times the number of loops per unit length times the length. And all of that gives us our final result, that the magnetic field is mu naught n I in the z direction. Actually, you see this is a positive result. That's because, in fact, we have a minus sign over here in our current enclosed. Again, that's a right-hand rule kind of convention. If we imagine that our loop here is going around anti-clockwise, then we would have a vector area with the vector pointing out of the page, whereas the current is going into the page, so we pick up a minus sign, and those two minus signs cancel. Okay, so that really was bookwork. What about the last part of the question? It says, using your answers, find the vector potential A outside the solenoid S greater than R. So this is the new bit. How are we going to do this? Well, nicely, we have a result for the vector potential in terms of the magnetic field flux. And we've just worked out the magnetic field. So we can use this result that the line integral of the vector potential around some closed loop is equal to the field flux enclosed, and this field flux is going to be the area of a circle of radius, let's say capital R. The capital R is the radius of our solenoid, times the field through that, which is B, which in the end is pi capital R squared mu naught n times the current I. So that's the magnetic field flux enclosed by some loop that is outside the cylinder. And it's important that the loop be outside of the cylinder because we've got to enclose the entire field flux coming through the solenoid. If we were talking about a loop that had a radius smaller than big R, then we'd only enclose part of the field, but here we're including all of the field flux. That's why I have a capital R pi capital R squared mu naught n times the current. Good. What about the left-hand side? Again, by symmetry arguments, we know that if we have a circular loop coaxial with the cable, then that's the same direction as the vector potential is pointing, and the vector potential is constant independent of angle. And what that gives us in the end is we can take out the vector potential A from this expression and multiply it by the circumference of the circle. And the loop is going to be of some radius s. So the loop here has a circumference of 2 pi times s. And as long as s is greater than capital R, it will enclose the entire field flux, which I've written on the right-hand side. And this is what we want, because we want to know what the vector potential is outside the solenoid. So here we've assumed that s is greater than R. And on the right-hand side, we have the entire field flux enclosed by this loop. And so just tidying this up a little bit, we can extract the magnitude of the vector potential as 1/2 mu naught ni, and then it's going to be R squared over s. If I want to write down the actual vector itself, a vector, then we know this is in the circumferential direction, so I can just put this in the phi hat direction. Okay, so that was a quick run through of the solutions to assignment 3.